we're back. We're going to look at part 3 of angular momentum, which is the conservation of angular momentum. So we're going to start just by picking up where we left off last time, essentially saying that a torque times a change in time, or applied over some amount of time, is going to give us a change in angular momentum, right? So speed up a rotating object, slow down a rotating object, etc. In this particular case, we're going to look at when the external torque is equal to 0, right? Implying that the change in angular momentum is 0. Or otherwise stated, the initial angular momentum is going to be the same as the final angular momentum, right? This is within a system, so what we define as a system. So let's take, for example, a disk that's rotating with omega, and then we've got a clump of clay that we're going to throw at the disk. Then, sometime later, right, this disk, well, still speed, we'll call this initial, we'll call this final, right? Gonna have clay attached to it. There's our blob of clay. So depending how we define our system is going to tell us whether momentum of our system is conserved. So if we look at this magic box with everything in the box, right, no external torque, everything is going to be conserved, right, because everything is in the magic box. Now, if that's not our magic box, and we pick our magic box just to be this, right, this is our system, then angular momentum won't be conserved because this is outside our box. Okay, outside influence. All right, so from here to here, this omega f is going to go down, right? Omega I, or it may not actually, we don't know until we look at it mathematically, but if you drop clay on it, you know, you can think about it reasonably, but it is going to change. So that momentum of the disk is not the same before and after. And in this case, momentum of the system is not the same before and after. But if we define, again, our system as this whole box, then afterwards, as long as everything is still in the box, our momentum is conserved, our angular momentum is conserved. Let's take a look at a problem. So a skater begins with her arms outstretched, as you can see here, right? Some distance away, and later on pulls her arms in. All right, so changing. So if you remember, I is mr squared. Okay, really there's a c in here, just a constant depending on the shape. So as r goes down, I will also go down. And so we can see in this case that Li equals Lf. Angular momentum before is angular momentum after. And that I initial, omega initial equals I final, omega final. So our initial is going to be 4 kilograms meter squared times our initial omega. So underline these guys for you. Okay, 10 rad per second. Our I final, 1 kilogram meter squared, times our omega final. Right, and you can see in this case then, the omega final is just going to be 4 times 10 divided by 1, or 40 kilogram meter squared rads per second. All right, so by decreasing that I, we're going to increase that omega much faster. And if you've ever seen skating before, you've seen that happen, right? That's how it works. So now the question is the kinetic energy greater or less than? Well, take a second to think about it, but we know that kinetic energy, at least rotational kinetic energy, is 1/2 I omega squared. So in the first case, we've got 4 times 10 squared and half of that. In the second case, we've got 1 times 40 squared, right? So we're going to have an increase in kinetic energy as arms go in. So why? Right, well, in order to pull the arms in, you have to do work. Okay, there was work done pulling the arms in. That's where that extra energy comes from. All right, so let's take a look at another problem. In this case, an artificial satellite, okay, is orbiting Earth, and we want to know at its greatest distance, okay, the satellite's moving a certain speed, and its closest distance moving a certain speed. And we want to know if the satellite speed at the perigee, which is the guy over here, this is a nice bright color, right, closest point, what its speed is compared to the apogee, which is this point over here. Well, we know there's no external torques here, and so Li equals Lf. Now, since this is an artificial satellite, like we said in one of the earlier videos, that means that L, okay, is going to be just mvr. And you can go back and see the derivation for that. But essentially that means m1 v1 r1 is going to equal, or let's call this initials rather, m final v final r final. And you can see right away that the mass does not change, and so we can drop those guys out, so we just have v and r. And so that means v final is just going to be v initial r initial over r final. All right, and if we substitute some numbers in for here, that means our initial vi is going to be 8,450. Our initial r is going to be 8.37 times 10 to the 6th, and our final r is going to be 25.1 times 10 to the 6th. So if you're taking a second to solve that, you should see that VF is going to work out to be 2818 meters per second. Right. And you could see that there was a decrease, right? And that comes right from, again, the R in this case. It's really the determining factor, how far you are and how fast you are going to move. All right. So now we can sort of change gears. It's still of the same idea, but we'll take a look at essentially an angular collision. Is what this works out to be. All right, so we have a uniform turntable of 0.5 meters and has a mass of 10 kilograms, rotational inertia that's given, and rotates at an angular speed of 4 pi radians per second. And the turntable bearing is frictionless, which means no external torque. It's not slowing down. All right. The AP exam really loves to talk about that frictional torque, though, but not in this problem. Okay, a lump of clay, a mass 2 kilograms. It's dropped onto the turntable from a small distance above and immediately sticks. So just like before, drawing a picture is great. So what we have is a disc. Okay, the disc has an omega, and it's a certain radius, right? And that radius is given. It is half a meter. Ooh, that is sloppy. Let's rewrite that. Okay, that radius is half a meter. All right, and then there is a lump of clay up top. And then sometime later, got that same disc except now the lump of clay is on it. And we want to know what the new omega is. Well, we solve it just like before. We know that Li is equal to Lf. All right, and so we have to think about the objects before and after. So before, what has an angular momentum? It's only the disk. The disk is the only thing that's spinning. So the moment of inertia of the disk and the omega of the disk, okay, initial, we can go ahead and I say disk, it's turntable. You put a disk on a turntable or a record. And then after, right, both of these are moving. And so once again, we have the turntable or the disk and its omega. But we also have this lump of clay. Now this lump of clay, okay, is sticking, it's just on, okay, the rim. That's the key. So if it's on the rim, it's on that outside. Now the nice thing is, right, we can go ahead and throw in, okay, the clay final, and the omega clay final. Now, these omegas have to be the same. Okay, they have to be the same. And the reason they have to be the same is because they're spinning together. And so we can go ahead and rewrite this. Now, we know where the turntable radius is. This is where the clay is dropped. We know the mass of the turntable. And so we can figure out all of these i's. Right, so the I for the disk, right, actually they tell us is 1.25 just 1.25 kilogram meter squared. We have to figure out the I of the clay. Well, if it's on the outside, it should just be mr squared. And so that should be 2 kilograms times 0.5 squared. All right, if you do that math really quick, all right, 0.5 squared is going to be 0.25, and you multiply that by 2, it's just going to be 1/2. Okay, or 0.5 kilogram meter squared. So now we can substitute all this in. Okay, give ourselves some space. 1.25 kilogram meter squared times our initial omega of 4 pi rads per second. Going to be equal to, again, 1.25 kilogram meter squared plus the 0.5 kilogram meter squared times omega final. And we'll find that omega final should work out to be 9 radians per second. All right, and again, that's the omega final for the clay and for the turntable. Now, we also can, if you wanted to, you could find what the linear speed of this clay is at the edge, and so on and so forth. All right, so we're going to move on to the last problem that we have for this. Another collision style problem where we're going to have two objects that are mashed together. All right, both of them are going to be spinning initially, then they're going to stick together after. So an engine flywheel, that's what these guys are, okay, has a rotational inertia of 0.4, that's going to be our A, and a clutch plate, this is the B guy, has a rotational inertia of 0.02. They're both initially at different angular speeds, then they're pushed together, forcing them to stick to one another, which means omega final is the same. Okay, we want to know what the final angular speed of the system is. Well, again, we can apply what we know Li equals Lf. Right? So you got to ask yourself before, how many angular momentums do we have? Well, we have the angular momentum of A, which is just IA omega A, and the angular momentum of B, which is IB omega B. And they're spinning the same direction. Right? So we can get IA omega A initial plus IB omega B all initial, right, equals, well, once they stick together, they got to rotate the same. So they're going to have the same omega final. So what we can do here is we can actually go in and substitute in our numbers, right? IA is going to be 0.04 kilograms. Omega A is going to be 50 rads per second, plus IB, which is going to be 0.02 rads per second, okay, times 200, right, not rads per second, kilogram meter squared. It's a moment of inertia. Okay, rads per second for this guy. And that's going to equal the sum of these two. So 0.06 kilogram meters squared. All I did was add them times omega final. And if you take a second to solve it, you should see omega final is going to work out to be, okay, 100 radians per second. And so that's all there really is to angular momentum other than some applied stuff, which we will get into in the next video. All right, see you then.